Welcome to a video on volumes. In the last video, I basically presented just three types of slicing: square cross sections, solid of revolution, and washer cross sections. This video is only focused on square cross sections. What you see in front of you is like a perspective drawing, and this is a square, even though it looks kind of like a diamond or a rhombus. And the way that this x-axis is drawn, it's actually going directly through, the middle of this square right here. And you could barely tell that just based on the way this is drawn. The x-axis is in front of this side of the square. Here's another view that might make it a little bit more clear. This is a dashed line. You could see I kind of erased a little bit of the line there. At this point, this becomes a solid line, so it's showing that you could actually see the x-axis if you could see it, actually. All right, but when it's inside the shape, you can't see it. So we're focusing on that cross-section that we get when we basically slice that shape. And I'll show you what that slice looks like in just a moment, but let's take a look at the example first. Oh, not the example, just the general idea of volume. So on your page, it says the integral from a to b of a of x dx. Can you find that? There's something missing. We need to say what this is. Well, this is volume. If you think about a stack of papers, you take one individual piece of paper, it seems like there's no volume to it because it's very thin. But once you stack up a bunch of pieces of paper, you get a ream, 500 sheets of paper, and that has volume. Well, that sheet of paper has volume too. It's just that the height of it or the thickness of it is very thin. So what we're doing here in this integral is we're adding up a bunch of these slices of area. So it could be a square slice, it could be a circle slice, it could be a donut slice. But we're adding them up from a to b. So these are x values. Well, I'm not going to write that, but the a and b are currently x values. We're going from left to right, and then the result is a volume. Okay, here's that example. That should be at the top or the bottom of your page. And I want to talk through it a little bit. So we're setting it up. One of the challenges with these questions is just some of the wording, especially this one. So we have a pyramid 3 meters high. A pyramid 3 meters high has congruent triangular sides. Congruent triangular sides. What in the world does that mean? Well, that means that the pyramid has triangular sides. So every side looks like this, and all of the sides are congruent. Now, we don't know what the base is until we read on. We see a triangular sides and a square base. Okay, great. Well, that means that when I sketch the pyramid, that the base is a square, and if I put it on its side, that means that the square is going to run vertically, which will be like what this is. Now, we don't know that just yet. All we know is that it's a square base. All right, so I'll just put a little square here. And this is the sides. All right, and then that's 3 meters on each side. Going back to that base, 3, 3, 3, 3. Okay, 3 meters on each side. And that's just one sentence, that's given us. It doesn't really help us with any of the calculus. All right, now each cross section of the pyramid, now we're thinking about the cross section. If a pyramid is standing up, like in Egypt, we're slicing it with a horizontal plane. We're taking kind of like a machete and slicing it sideways with our arm. So each cross section of the pyramid is parallel to the base. Each cross section of the pyramid parallel to the base. That means that, again, if the base is on the ground, we're slicing in such a way that it's parallel to the ground. But if we take that entire pyramid and we put it on a coordinate plane, we're putting it on there sideways. And then the goal is to find the volume of the pyramid. All right, this piece right here, each cross section of the pyramid parallel to the base is a square. Let's take a look at what that would look like. Now I take that pyramid that we're talking about that has a square base, I put the top of it at the origin, and I'm just sketching in such a way that I could see it. Now this is not hugely important that you get this picture perfect, and you could just draw it from left to right without any perspective, but when we're talking about the cross section, we're talking about this piece right here. Yeah, you can see the imperfections in my square, right? And notice that at first I sketched the dashed line to the x-axis, but then I realized that I'm actually sketching it down to this dotted line down here. I'm going to try another one of those. Man, seems like they get worse and worse, right? All right, try another one. Oh, I have to go down straight. That's what I need to do. Perfectly vertical. Okay. See if I could fix some of these. I'm going to try this again. I'm going to go straight down. Straight down there. There we go. That's a little better. And diagonal at the top, straight down to the dashed line. Okay. All right, now just another kind of thought about this shape that we're looking at, that if I were standing over here on the right and I was looking at the bottom of this pyramid, all I would see is a square. And this side right here is at the utmost top, like the very top, and this is the bottom. So if I were to kind of measure this shape from bottom to top, I would measure straight up like so. And what it tells us in the problem setup is that this is a 3 by 3 base. So I could go back to that, and I could say, all right, the 3 by 3, that's 3 there, that's 3 there, that's 3 there, that's 3 there. Lots of 3s. At this point, you might think, wow, is this what's required for each question, to think about this so much and then sketch it and then try to work out all this? Well, there might be a few like that, but not everyone is like that. All right, let's go back to the question. Now, the way that we'll actually do the calculus related to this is we try our best to create a sketch, and there are really only two versions of this particular square cross-section. The one where we have it kind of like a square, a normal square, like this one, or you have a square on its side so it looks like a diagonal. And I think that's going to be the one like your homework. I'll put a question mark. Okay. And now the next step is to think about the formula for a of x. Well, the formula for a square is side squared, right? And so if we do that in terms of x, we have the area in terms of x is x squared. And truly, that's it. Now, thinking about the limits of integration, let's go back to the question. It says a pyramid 3 meters high, that could be 4, 5, 6, whatever. That means that that pyramid 3 meters high is from the origin all the way to the right here. And that's what that blue, black 3 is right there. So that means our limits of integration are a equals 0 and b equals 3. And then we could just set up the integral and evaluate it. So what that looks like is volume equals the integral from 0 to 3 of x squared dx. Hey, that's a happy place. That's the thing that we like doing. It's taking the antiderivative and evaluating using the fundamental theorem of calculus. Let's do that right now. The volume equals x cubed over 3, evaluated from 0 to 3. So that's 3 cubed over 3 minus 0 cubed over 3, f of b minus f of a. So that's 27 over 3, which is 9 meters cubed. That's it for that one. So that's just one example about square cross sections. Thanks so much for watching.